Hi guys, this is a recording meant to help you review Lecture 1 materials. So in Lecture 1, we covered what is chemistry, and we talked about the science of matter. We started with the question of what is chemistry. So chemistry is the study of matter, its composition, structure, properties, and the changes it undergoes. And then we also included in that the study of energy, and as far as energy interacts with matter. And so that's where we're really worried about in chemistry. So what is matter doing? And we defined matter as anything that occupies space and has mass. And then talked about composition of matter, and that all matter is composed of atoms. We talked a little bit about atoms, and that the atom is the smallest particle of an element that retains the chemical properties of the element. And that scientists used to think the atom itself was indivisible, was the smallest unit of existence, but now we know the atom can be split into smaller pieces, such as occurs in nuclear bombs or in fission and fusion reactions. There are 118 elements that have been observed thus far. We haven't gone too much into what differentiates these just yet, but we'll get to that pretty quickly. We did discuss the differences in types of matter and classes of matter. So all matter can be broken down into either pure substances or a mixture of substances. And then pure substances can be broken down further into elemental species. So these are species that only contain a single element. That doesn't mean the element isn't bonded to itself. It just means there's one element present. So for example, in a gold ring that's 24 carats, all you have is gold in that. It's the only element. All those gold atoms are bonded to each other, but we still call this a pure element. And then a compound would be something like water, where you have hydrogen and oxygen stuck together to make a water molecule. Now, water or a compound can still be a pure substance if there's only one compound present. So water can be extremely pure. You can get all of the salt and other stuff out of it, and it would count as a pure compound. We also talked about homogeneous and heterogeneous mixtures. So in a homogeneous mixture, you have two or more pure substances mixed together. Most of the time, you actually have at least 100 different species, if not more, present in anything. If you filter things out, you can get it a lot better. But in most things, like drinking water, you have salts, but you also have various organic molecules left behind by bacteria and plants that aren't filtered out before you drink the water. The example we talked about in class was vinegar. So in vinegar, you have acetic acid and water mixed together. And because you can't look at one spot on this oil, so let's take this yellow bottle of oil, for example. If I look where the red spot is right now, and then I look where the red spot is now, you'll notice I moved it, the oil looks the same in both spots. And so we can say that's a homogeneous mixture. A heterogeneous mixture would be something like salad dressing, like this, where you have big chunks, or you have regions that are distinctly different from other regions. And I mentioned in class that things that students get mixed up on sometimes are things like ketchup and mustard that have some amount of texture to them. And these are homogeneous as long as you can't look at one spot and another spot and tell a difference. So for example, yellow mustard is homogeneous. Every spot is yellow and looks the same, whereas most brown mustards that have seeds in them are a heterogeneous mixture, where you can see spots where there's seeds and spots where there's not. So we also had an iClicker quiz, and we asked, is P4, also known as white phosphorus, a pure substance or a mixture? And is it an element or a compound? Right, so this is a review question from the previous slide. So white phosphorus, P4. If you're trying to review this material, go ahead and pause the video now and try and work through this, and then I'll give you the answer in a second. Okay, the answer is that it's a pure substance and an element. So most people can get that it's a pure substance, correct, because I'm not listing it with anything else like water or any other components there, no salts or anything. But people often do get this confused with a compound because they see P4 there. That says that there's 4 phosphorus atoms, and they're all stuck together and bonded. So people think they're bonded, they're compounded. But that's incorrect. That's not the right way of thinking about this. A compound is when 2 or more species or 2 or more different elements are stuck together. If there's only one element present, then we call it an elemental species. We talked also about properties of matter. We talked about chemical and physical properties. Now, chemical properties can only really be determined by reacting a chemical with other chemicals. So chemical properties are, how does this chemical behave with other chemicals? Or how does it behave in a reaction? Some chemicals can actually react without any other chemicals present. They can break down, for example, into gas or other things. Or they can be broken down by sunlight, such as how posters will fade or pictures will fade if they're left in the sun. And then physical properties are things you can measure about the material without having to change it. Things like color, odor, density, electric conductivity, solubility, etc. Now there are a few questions about these, and I will try and address those. But before that, we broke these physical properties into intensive and extensive properties. So intensive properties are things that can be measured that are always the same despite how many things are there or how much of a substance is there. So for example, the color of these gold bars is not going to depend on how many gold bars are present. The weight of these gold bars is going to depend on how many is present. The density of the bars, which is a measure of mass divided by volume, the density is going to remain the same no matter how many bars are present, even though it depends on 2 extensive properties, weight and volume. And because it's a ratio of those 2 things, of weight and volume, that ratio can actually turn it into an intensive property. So intensive properties can depend on extensive properties, and extensive properties can depend on intensive properties. Okay, and then we moved on to talk about physical states of matter. Specifically, we talked about solids, liquids, and gases. There are a few other states of matter, and depending on how you look at that philosophically, there's more or less, but we're mostly concerned about solids, liquids, and gases. Now, a solid has a distinct volume and distinct shape. A liquid has a distinct volume and no distinct shape, and it assumes the shape of the container, and a gas has no distinct volume, no distinct shape, and expands to fill the container. So the example I gave in class is with ice. If you put ice in a beaker, that ice is not going to do anything. It's going to maintain its shape, and it's going to maintain its volume. As you heat that beaker up, however, and the ice melts and becomes a liquid, what happens? It spreads out and fills the base of the beaker as full as it can get. It's not going to expand to fill the beaker. The liquid has a distinct volume, and the liquids actually don't like to be compressed or expanded very much. They're pretty resistant to that. And so actually, if you put water in outer space, it actually will stick together and retain the same volume for a while until it either loses enough heat to turn into gas or loses enough heat to turn into ice or gains enough heat from the sun, which is actually the more likely scenario to turn into gas. And so if you have ice, or if you have this water in a beaker, you heat it up farther, it turns into a gas, then it will expand into the gas or into the room you're in and try and fill the entire room and spread out as much as it can. So it doesn't have a distinct volume or shape. We also covered changes in state. These are phase changes. And I said that you do need to memorize all of these changes, okay? And you need to be very careful and conscious about when you use the different descriptors. So for example, a solid going to a liquid is always melting, and a liquid going to a solid is always freezing. You're familiar with that one. One that does get people into trouble is a liquid going to a gas is vaporization. A solid going to a gas is not vaporization. So a solid going to a gas is sublimation. And the example I gave here was putting clothes on a clothesline in cold weather. So in cold weather, such as in northern Idaho, you put clothes on a clothesline, the clothes will freeze, but then over time, the ice in those clothes will sublimate away, and you'll be left with dry clothes. The water didn't vaporize because it was in a solid state and went to a gas state. So a liquid going to a gas is vaporization. And then a gas going down to a liquid, of course, would be condensation. That's what you see on your glass when you have cold water in it, right? That's the reason coasters were invented. And then the last transition you'll need to memorize is a gas going to a solid. That's deposition. So that's what you see in your freezer when you get ice buildup. You don't get those oftentimes in the fridge or the freezer on your fridge, but you'll see it in bigger freezers a lot. And in that case, you have gaseous water that turns straight into a solid or into ice without ever going through the liquid phase. And all of these transitions, we tend to think of these transitions in terms of water a lot, but in terms, or for some species, sublimation is much more common than melting and vaporization, and deposition can be much more common. Deposition, of course, is what happens when frost forms on your lawn as well. And then we went into physical changes and talked a little about that. So physical change is when you change a material, but you don't change its chemical makeup. You don't change it at the atomic or molecular level. You're just changing it at the macroscopic level, right? You can crush ice. You can rearrange your pillows on a couch, right? And that's a physical process. And we also talked about chemical reactions or chemical processes. And these occur when you affect something at the atomic or molecular level. So where you're breaking bonds, reforming bonds, or changing the arrangement of atoms and molecules. So we had some practice questions here to see if you could figure this out. If you would like to go ahead and pause here, feel free, and then I'll go over the answers in a second. All right, so I'm going to go over all of these answers at the same time. So if you didn't go through all the problems yet, go ahead and pause the video again. But milk souring, is that a physical process or a chemical reaction? Well, you'll notice that the consistency of milk changes and the smell changes. Those are pretty good indications that this is a chemical reaction. What's happening is bacteria in the milk is breaking down the materials in the milk, converting it to other stuff. And bacteria uses chemical reactions either within or actually sometimes without the cell wall of the bacteria to cause these reactions. All right, the lawn is mowed, chemical or physical. Well, we're not actually breaking any bonds. We're just cutting the grass, so we're changing its length. And so as one person pointed out, well, we cut the lawn and then the trimmings go on to rot or decay. So aren't we causing a chemical reaction? Well, the answer is yes, we are causing a chemical reaction, but cutting the lawn is not a chemical reaction. That's a physical process. The other example they brought up was, what if I bite an apple? If I bite an apple, it can then go bad, whereas if I don't bite it, it doesn't go bad. That's true, but biting the apple is a physical process. You're not breaking any bonds or even changing the chemical makeup of the fruit at all. You're biting the apple and then setting it out, and then you're creating an environment where it can undergo chemical reactions with the air. So chemical reactions can lead to physical processes and vice versa. But when we're talking about specific things, we want to be able to separate them as either chemical or physical. So the next example, wool is spun into yarn. This is a physical process. It involves no chemical reactions. You're just changing the arrangement that the wool, the fibers in the wool, are arranged relative to each other. So you're putting them in a more convenient position relative to each other so that it's more comfortable or more useful. A great example is if you have a bunch of pillows on a couch, if you rearrange them, that's clearly not a chemical reaction. but a physical process where you're moving things. And that's the exact same thing that's happening in wool being spun into yarn. You're just rearranging things. Water boiling. Okay, now phase transitions get tricky for some people, but the question is, have you broken any bonds? Have you changed anything at the molecular level? In other words, if I boil this, can I collect that gaseous water and cause it to condense and still have water? The answer is yes. And so phase transitions are considered a physical process. You're not changing anything at the molecular level. You're just changing how everything is positioned relative to the other water molecules. And the last one, silver utensils tarnishing. This is a chemical reaction. This is where oxygen actually bonds to the surface of your silver utensils. This is actually a really slow but constant reaction. So anytime you have silver in open atmosphere, it's actively tarnishing, but it's such a slow reaction that you don't notice this process happening until a long time has passed. And then we moved on to talk about energy, the three types of energy. So energy in science is generally defined as the ability to do work. So the three kinds of energy we use, so we use this snowboarder to describe the types of energy. And the first was potential energy. So potential energy is another way of saying stored energy, or energy that isn't being used right now but can be later. So as the snowboard reaches the height of this ramp or this jump, I don't know, I'm sure there's a real word in snowboarding and skateboarding for this. But when the snowboarder is at the top of this, they've stopped moving. All their kinetic energy or their motion energy has been turned into potential energy, and then they'll start falling again. And that fall will turn their potential energy into kinetic energy, which is the energy of motion. And then the last type of energy is radiant energy, which is only really observed in the form of light. Now, if you ask a physicist what I just said, they might say, that's not true, there's other forms of radiant energy. In chemistry, though, we generally consider light to be the only form of radiant energy. And somebody might ask, well, what about fire? Isn't that type of energy? Well, what you're seeing is radiant energy, which is light being released from a chemical reaction that's actually happening exactly where you see that flame. So what happens in a fire is actually the materials that's burning is actually turned into a gas and then reacts with the air after it's left the solid. That's why flames aren't occurring on the object itself, but usually above it as things vaporize or sublimate into atmosphere, depending on what fuel you're using. Now, energy can neither be created nor destroyed. It can be turned from one form to the other. The example I gave in class was if you take a battery, it's full of potential energy. You put it into a flashlight. That potential energy is then turned into kinetic energy for electrons that flow through a wire. And as those electrons flow through the wire, they go to some light source, either a metal filament or an LED. And then that LED takes the kinetic energy away from the electrons and converts it into radiant energy and gives off light. And we'll talk a little bit more about that process as the class goes on. Some people asked, what about heat? What about heat caused by friction? And questions like that. And I feel like I can give you a much better answer later in the class when we actually talk about heat. Because heat isn't actually energy. Heat is a measure of how much energy is present, which is slightly different. And as we get into that, you'll understand that a lot better. I promise that by the end of this course, everyone will understand the difference between heat and energy, or at least how they're related. Okay, we then went on to talk about the law of conservation of mass, and we talked about this guy, Lavoisier, who is a French chemist who really helped get chemistry going. And in his time, scientists believed in something called phlogiston, or the fire element, which existed in matter, and that some matter contained a lot of phlogiston, some matter contained less, and that when you burned matter, it would release this phlogiston. So when you burned wood, it would release phlogiston, And once all the phlogiston was gone, it would stop burning. But then Lavoisier found that if you burned metal and phosphorus together, the mass of the reaction, or the mass of the metal and phosphorus, actually increased. Now, if you're releasing phlogiston, your mass should decrease because you're releasing stuff. But he found that he gained something. So he said, I think the phlogiston idea is garbage. Let's just throw it out. And that's largely what we've done. So what he started doing was studying combustion reactions, or started burning things inside sealed containers. And he found that, and I'm quoting him here, an equal quantity of matter exists both before and after the experiment. And I realize I'm not exactly quoting him because he's French and I don't speak French, but that's basically what he said. And he found that oxygen was actually required for fire. And so when you burn things like wood, and large quantities of the wood are sublimated into the atmosphere and then react with oxygen in the flame, that yes, you are losing material. When you burn wood, it does get lighter. But when you burn this metal, it's not sublimating. It's just causing oxygen to rapidly deposit onto the surface of the metal, or to oxidate the phosphorus. All right. So then the question is, Lavoisier's work with burning objects helped prove what? So go ahead and pause the video. Okay, it helped to prove the law of conservation of mass. If you don't understand that, go ahead and rewatch the video about the previous slide, or make sure to ask somebody. So a good rule of thumb for being successful in any class, but especially in chemistry, is anytime you get a question wrong, record it. Record the question in a notebook or somewhere so that you can know, I didn't do good on this, right? You don't want to build up confidence that shouldn't be there in understanding materials. So if you did miss something, that's a great way to record what you're weak on. Then you can go and improve on it. So if you can do that, you can actually be very successful, even though initially you might get the questions wrong. As long as you can review them and teach yourself, that's a very good way of learning things. All right, next we talked about another French chemist, Mr. Proust, who also studied reactions between metal and oxygen. We didn't actually get this far with both lectures, but Proust found that in a given chemical compound, the proportions by mass of elements that compose it are fixed. And I did a bad job reading that, but basically what that meant was he found that he could mix tin, which is elemental symbol is SN for historical reasons. He found that he could make a compound out of tin and oxygen that was 88% tin and 12% oxygen, or he could make one that was 79% tin and 21% oxygen, but he couldn't make one that was 85% tin and 15% oxygen. Now, he didn't quite figure this out. He laid the groundwork for a lot of knowledge we have now. Unfortunately, he didn't get to the point by himself that the reason for this was because of atoms, right? You can only attach either one atom or two atoms of oxygen to tin, which can't add 1.5 atoms of oxygen to tin. It just doesn't work that way. Atoms in chemical reactions are generally indivisible, right? We can do special stuff like nuclear bombs to break them apart, but atoms in and of themselves, for the most part, we think is stable, indivisible. It wasn't until John Dalton came along a little while later, wherein he pointed out a compound forms from its elements through the combination of atoms of unlike elements in small whole number ratios. Now, this was a big point. This small whole number ratios thing really proved critical because it helped us understand the difference between carbon monoxide, so CO, and carbon dioxide, CO2, things like that. Now, this whole number ratios idea is still fundamental for chemistry. It's still there because atoms have to attach in whole atoms. Unfortunately, the small part of this statement isn't necessarily true. It doesn't have to be small whole number ratios. It can be very big whole number ratios. So for example, in some proteins, you can have thousands of atoms of carbon, thousands of atoms of hydrogen, hundreds of oxygen and nitrogen, then 5 or 10 chlorines or fluorines or sulfurs, various other atoms inside these proteins at very small rate or very small values relative to how many carbons are there. So it's not a small ratio. It can be very big ratios. But this was evidence of atoms. And it was really the thing that started spurring people on. It wasn't definitive. Not everyone believed in atoms at that point. That didn't come till a little bit later, but he really laid a lot of groundwork for that idea. All right, so here's a quiz to see if you understand the law of multiple proportions. So go ahead and pause the video, see if you can figure out which of these illustrates the law of multiple proportions. All right, so the options are the mass of NO2 is twice the mass of NO. That's actually not true, so it's not the answer. The ratio of O to N in NO2 is twice that in NO. It's true that there are twice as many oxygens in NO2 as there are in NO. So that is the law of multiple proportions. So it's a whole number difference. There's twice as much. All right, for C, NO2 always contains one nitrogen atom and two oxygen atoms. So that is true. That's more the law of definite proportions, though, not multiple proportions. NO and NO2 have similar chemical and physical properties. Well, that might be true. It's not really that true, but it has nothing to do with the law of multiple proportions. And lastly, for E, NO2 and N2O4 are the same compound. That's just false. And that's the kind of nonsense you get from the science babe on Facebook or something. It's just nonsense. So our answer here is B. Multiple proportions say that you can have either one oxygen or two oxygens or three oxygens attached to a nitrogen, but you can't have 1.5 or a half oxygen attached to nitrogen. You can get very complex numbers of, let's say, 30 of one element and 31 of another element, things like that. But they all have to be in whole numbers, whole atoms. And that's really what the law of multiple proportions is getting. All right, here is another question, another review question that'll help us get into more of the molecular view now, as we've gone from bulk properties, and we're going to start getting into atomic and molecular properties. But sucrose, which is table sugar, can be obtained from sugar cane or sugar beets. Either way, it has a chemical formula of C12H22O11. You'll notice here that this is not exactly a small ratio of atoms relative to each other, 11/22, 11/12, etc. But this observation illustrates which law. So go ahead, I know I broke that that question in the middle, so go ahead and reread it, try and figure this one out. All right, so this is showing us the law of definite proportions, right? You have to add 12 carbons, 22 hydrogens, and 11 oxygens to get sucrose, and sucrose has that exact same ratio of atoms, whether you get it from one source or another. So people often talk about whether synthetic vitamins are actually healthy for you or if natural vitamins are more healthy. So the answer is synthetic and natural vitamins are identical. There is a concern about other byproducts. So when you make a synthetic vitamin, you often make other things at the same time that you don't mean to make, which can be less healthy. I'm not a nutrition scientist, so I don't know all the ins and outs of synthetic versus natural vitamins and supplements, but there you go. Now, I showed you the formula for sucrose right here, C12H22O11, but that's actually not a very descriptive formula. That's actually the formula for a whole host of chemical compounds. What you really need is something to indicate how the atoms are bonded to each other. So we'll often draw out structures where we can show exactly which atoms are bonded to each other, and we'll get into this structure, or not this specific structure, but drawing structures a little bit more in a sec. But even this structure isn't actually the structure of only a single molecule, because you see this OH group, and this OH group, and these two over here, well, those can actually either face into the screen or face out. So in other words, they have different orientations they can face inside the molecule. And whether they're facing in or out actually significantly affects the chemical properties of this molecule. And so then you have to draw, if you want to be more specific, this is what I've drawn here is actually the structure of, let's see, 2, 4, 8, 16 different sugars. Oh, and I missed one OH right here. So this is actually the structure of 32 different sugars. So if we want to be more specific on that, we'd have to draw either with dashed arrows or with solid arrows and indicate whether these different groups are facing towards us or facing away from us. And we'll get a little more into that as we go on. But this raises the point of how do we talk about molecules? How do we talk about different chemical species? How do we indicate what we're talking about? So often, depending on the context, you can just give the molecular formula. You'd usually say the name of the compound or something like that, and then you give the formula and people say, yeah, I know what that is. But in cases like this, in a general chemistry class where I could put C3H6O and ask you to draw that, you'd have no idea which carbons are bonded to the oxygen, etc. And we'll get into all of that later. But I'm just trying to illustrate the point that you really have to draw it out. So for example, here, I've drawn out one possible structure corresponding to this formula where the carbon or the central carbon is double bonded to that oxygen. And over here for this other formula, C2H4O2, I've drawn another formula or another structure, but these aren't the only possible structures for these formulas. But drawing formulas or structure formulas like this can be both time consuming and take up a lot of space on things. So often we'll condense them as much as possible. And we'll get into a few ways of condensing these formulas. One way is just to draw all the hydrogens just right next to the carbon, so not draw those bonds. So we know hydrogen only makes one bond. So if you draw it next to something else, that's saying it's bonded to that thing. And there's no actual ambiguity here in either of these. They are very clear in which structure you're talking about. They don't give you a good three-dimensional representation though, so you can represent it as a ball and stick model. And then this gives you kind of a better view of what these guys look at like in three-dimensional space. Though real molecules don't have sticks between the different atoms holding them together. Real molecules are more squished together like this. And actually, as we'll get into it towards the end of this class, even this view of the molecule is actually pretty wrong. It's pretty useful for thinking about molecules, but it's actually surprisingly wrong in a very confusing and complex way. So get ready for that. All right, so all of this work that's been done historically by scientists like Lavoisier and Proust and Dalton really helped formulate and cement the scientific method. And of course, chemists were actually a little late to the game. The scientific method was really being worked out by physicists and natural philosophers, which evolved into biologists and ecologists and things like that. But in the scientific method, what you do is you make an observation. So you see something, and then you try and think, how does that work? You come up with a guess, which is your hypothesis. Then you take that hypothesis and you do an experiment. You try and design an experiment to disprove your hypothesis or to see if your experiment will be accurate or consistent with your hypothesis. If you do this enough times and you have enough experimental evidence, then that becomes a theory. So a lot of times people confuse a theory with a hypothesis, but theory is actually more grounded in experiment. It's something that's generally accepted as true. There might be problems with the theory, but it's generally got enough backbone in it that you can use it for things, right? And then if that theory continues to hold up under more experiments, it can then become either a theory or you can get a scientific law. Or a general theory, a more general theory that is used more broadly. So the difference then between a scientific law and a scientific theory is that a law is a concise summary of accepted facts of nature. So for example, the boiling point of water at sea level is 100 degrees Celsius. That's a scientific law. And then the theory would be what explains why is it 100 degrees Celsius at sea level? Why is it different? Different elevations. So the scientific law is what is always observed. And then the theory is why is it observed? So it's a concise, well-tested explanation of why a natural phenomenon is observed, or why a scientific theory is true. Nope, that last part is false. I thought I cut that out. So you can't have the definition or the words in its own definition. Anyways, let me know if you have any questions with that, and I will start posting videos like this for all of the lectures in the future.